Okay, now we're back for quadratics, right? What tells you that something is a quadratic? It's when the degree of the function, the highest exponent, is 2 or 4 or 6 or 8, an even number, right? Most of the ones you'll see are going to be 2, something in the form of y equals x squared. So how do we know something's linear? If the highest degree is 1. No y's are squared, no x's are squared, nothing is to the 1/2 power or the negative 1/3 power, right? All of your variables are to the first power. So if we think about a standard form, just like a while ago when I wrote ax plus by equals c for a line, for standard form of a linear equation, we've got a standard form of a parabola, of a quadratic equation as well. And that's usually ax squared plus bx plus c. Either f of x equals that or y equals that. And here again, don't get it, it's all letters, but remember that the capital letters here, A and B and C, are just standing for constants. X and Y are the variables. And if we had real numbers in there for A, B, and C, the solution set, if I plotted all the numbers, X and Y, all the ordered pairs, X and Y, that made this thing true, they won't fit on a line anymore. They fit on a parabola. That parabola might be going up, might be going down, might be wide, might be skinny, but they fit that basic parabolic shape. Similarly, if I had a function that's to an odd power, x cubed or x fifth, no longer am I dealing with a line, no longer am I dealing with a parabola. I'm dealing with something like this, right? And it's going to have 2 turning points if it's to the power of 3, that at most 2 turning points. If it's the power of 5, it'll have at most 3 turning points, right? So there's lots of stuff we can learn from the basic structure of the function itself. We can start to guess at the graph without a graphing calculator. So if you're ever stuck on a desert island and you need to graph something, this is what you need to know. All right. So if just like slope-intercept formula is really handy if I want to graph a line, being able to change a quadratic equation into some other form where at a glance I can learn something about that graph is really handy. We know that slope doesn't mean anything, or at least it doesn't mean anything yet. It will in calculus. It doesn't mean anything for a parabola. But what we do know is that parabolas have a vertex somewhere. They open up, they open down. We can find their zeros where they cross the x and y axes, and their intercepts. And so let's figure out a way to do that. Let's find a way to get into to what we call vertex form. So I'm going to change things up here. This is our standard form, and what we're aiming for is this. Here again, don't mind that they're lowercase letters here. A, H, and K are constants. And you're not quite seeing this. Yeah, you are. Okay. A, H, and K are all constants, unique to this one quadratic equation. All right, that is vertex form. At a glance, I can tell if A is positive, the thing opens upward. If it's negative, it opens downward. If it's greater than 1, it's a tighter parabola, narrower. If it's between 0 and 1, so a fraction like 1/2, 1/3, 1/8, 2/9, whatever, but between 0 and 1, that widens the parabola out, makes it a little flatter like this. My vertex is at H and K. So all of a sudden, I know a lot about this parabola. I know where it starts. I know where its point is, if you will. I know whether it's going up or down. And then I could use any of the methods I know how to solve quadratics by setting it equal to 0 over here. I could use the quadratic formula, I could factor it if it's factorable, or I can complete the square to find out where the zeros are, that is where it crosses the x-axis. And if I plug in x equals 0, then I find out where my y-intercept is. So I can learn a lot about this graph by knowing how to, again, manipulate it algebraically. So let's take an example and convert it from standard form to this vertex form. In fact, let's use this example up here, okay? I know it's a lot of letters, but let's see, we can do this. It's just algebra. Don't break any rules. The only thing we're assuming here is that none of these coefficients, A, B, or C, I guess C could be 0, but we're assuming they're not 0, okay? Because if you start dividing by 0, then we get in trouble. Okay, let's use an example first, actually, that's got real numbers in it, not this one. I'll show you why. Okay, so I get f of x equals x squared plus 6x minus 4. And I might say, oh, maybe I can factor that. Well, the only factors of 4 are 2 and 2 and 4 and 1. And I got to have one positive, one negative. And there's no way that 2 and 2 and 4 and 1 subtracted from each other is ever going to give me 6. So I know that I can't force that to be a perfect square right now. So I'm going to use completing the square, that technique, to force it into this format, into the vertex form. Completing the square, I first have to get this constant term out of the way, put it by itself, okay? So f of x equals x squared plus 6x plus blank minus 4, right? I didn't throw it away, I just moved it over here to the side. Importantly, I cheated a minute ago. I said the first thing I need to do is get it out of the way. First thing you need to do is make sure that your coefficient, your lead coefficient, the coefficient goes with the x squared term, is 1. Here in this case it is. That makes it easy. I can show you how to deal with that if it's not later. So now, ignore the negative 4 for a second. I'm going to look at this bit here and do what I know how to do to complete the square. You know that. Take half the middle coefficient and square it, right? So half of 6 is 3. 3 squared is 9. I add a 9 here, but I can't just add a 9 and leave it alone. I've cheated, right? So I either have to add a 9 over here. Well, that looks ugly. I'm going to subtract a 9 on this side, right? So my net effect on this function is 0. I haven't added or taken anything away from it. I just move things around. I've done some algebraic magic. So now I know that by design, this thing factors to a perfect square. X plus 3 quantity squared minus 13 over here. So I've got a parabola where my vertex is at negative 3, because there's a negative built in to this vertex form, right? And I have to think, okay, what would make this 0? What would move that parabola back to the origin in the parentheses? Negative 3 and negative 13. That means my parabola is opening up because my lead coefficient is positive, and it's not squeezed or flattened. So normally I would have a parabola starting at 0, 0. Well, now I've got an upward parabola moved back 3 and down 13. So somewhere down here it starts and it goes upwards. And if I want to find where it crosses the x-axis, then I can take this form of it and set f of x equals 0, right? Because y equals 0 describes every coordinate on the x-axis. So I can set that equal to 0 and solve this equation here to find what those x values are. If I plug 0 in here, I can find out, for x, I can find out where my y-intercept is. So if I plug 0 in here, I get 0 plus 3, that's 3. I square that, I get 9. 9 minus 13 gives me negative 4. So I know that this thing crosses the y-axis somewhere down here at negative 4. And it's doing something like that. Okay, so I'll stop there. I gotta meet with a student now.